This lecture is called Explain Gravity the Situation. It's one of my favorite quotes. You may hate gravity, but gravity doesn't care. So, we want to look at what causes gravity in one extent and how we can calculate gravitational attraction. So, I want to look at just a brief overview of what our current view of gravity is. You'll see these green and black squares represent something that we call space time. And whenever you have an object with a large amount of mass, you see it produces these ripples in space-time. And what that actually represents is that's the gravitational force. And you can see this for a star, it can produce an enormous amounts of gravitational force as it turns and collapses into a black hole. So our goals are number one, that you be able to describe the effect of distance on gravitational force. Number two, that you be able to describe the effect of mass on gravitational force, and that you be able to use that equation right there, which is called Newton's law of universal gravitation. So the weight of attraction. There is an attraction between any two objects with mass called gravity. So whenever you jump out of a plane and you're falling down, that right there represents an attraction between you and the planet Earth. That means that the Earth is attracted towards you a little bit as well. Now, it's not the Earth is too big to matter, um, but you accelerate quite a bit as a result. Now, if you look at the picture to the right, what that represents is that represents the attraction that the Earth has to the Sun. Because as small as you are compared to the Earth is extremely small compared to the Sun. And so as a result, the Earth is attracted to the Sun and goes in an orbital pattern around it. What you did is you saw that force and mass, or gravitational force and mass, were directly proportional. So increasing the mass from 1 to 2 doubles the gravitational force. And likewise, you saw that the distance and force graph was in an inverse square relationship. So if you double the distance, you actually decrease the force by a factor of 4. So we learned about that already, and what we can see now is that Newton took these ideas right here and he put them in his version of what's now known as Newton's law of universal gravitation. So to refresh you, Newton said, if I've seen further by standing, it's by standing on the shoulder of giants. Newton came up with this idea that the forces were proportional. And now the reason why he said the forces were proportional is because this term right here, which was in the equation, wasn't there yet. Okay, Newton didn't know about this G term. Okay, we now know it's there, but Newton thought there was going to be some sort of term, but he had no idea how he was possibly going to measure it at this point. So he left it off, and his version was that F was proportional. That's what this fish sign stands for, to m1 m2 over d squared. So what that means is if you increase the mass, the force goes up proportionally. If you increase the distance, the force goes down by a proportionate square. So this has the makings of an equation, but it's no means a complete equation because it lacks that equal sign. So, using Newton's version, we can answer some questions, but people say, well, if Newton couldn't turn it into his own law that it's named after him, why is he considered a genius? And the reason for that is he was the first one to realize that it could be universally applied. In other words, the reason why an apple falls to the earth is the same reason why the moon goes around the earth. Okay, they are both having to do with the gravitational attraction. Now, the reason why the moon doesn't fall straight to the earth like, say, the apple does is because the moon itself, the earth moves, and so the moon misses it. The moon is constantly trying to fall towards the earth, and the earth is constantly moving out of its way. So we come to our first example. It says the mass of an Earth increases every year from falling asteroids, comets, dust. How many years would it take for the gravitational force to increase by 10% if this is the mass of the Earth and this is how much debris strikes the Earth every year? Realize that according to Newton's formula, this F is proportional to m1 m2 over d squared. Any increase in the mass of the Earth will likewise be reflected in an increase in the gravitational force. So if I want to increase the gravitational force by 10%, I need to increase the mass by 10%. And a 10% increase in this case would be 5.98 times 10 to the 23rd. Now, if you're wondering where I got that from, remember 10% is 0.1. 0.1 times the mass of the Earth, 5.89 times 10 to the 24th, would give you 5.98 times 10 to the 23rd. So this is what mass I want to increase. Now I actually have a ratio here that says there's 2 times 10 to the 9th kilograms of debris that strikes it every year. So all you have to do is divide and say 2 times 10 to the ninth kilograms per year, and you will get the value of, or how many years it's going to take for this to work, because kilograms is going to cancel with kilograms and years is going to flip its way to the top. So when you take 5.98 times 10 to the 23rd and divide by 2 times 10 to the ninth, you get something like 2.99 times 10 to the 14th. And remember, this is in years. So you're talking about 299 or 299 trillion years. So it's a long way off and not likely to happen. So example A2 says a comet experiences a force of F when separated by a distance d. So we'll draw our comet here, and we'll say that this is a distance d, and they have a force of F between them. Now it says when the comet reaches, it loses a third of its mass. As it gets closer, its mass is now no longer m, but instead it's m over 3. And then now we say that the distance though is a quarter as much. So as it gets to a quarter of the distance, it's lost a third of its mass. It wants to know what the new gravitational force is. The easiest way to do these questions is this. We're saying F is proportional to m1, m2 over d squared. Plug in 1 for everything for the first go around. So the original F is 1, the original M is 1, the original D is 1. So 1 is proportional to 1 times 1 divided by 1 squared. And you say, well, that's pointless. Why would I do that? Because now when we take a look at it, let's take a look at the new terms. Now we don't know what F is. We're trying to figure out what that is. But we can say F is proportional to the comet's mass, which is now 1/3. Because it was 1 and now it's a third of that value. So now it's 1/3. Excuse me, it was losing 1/3 of its mass. So it should be 2/3. I'm sorry. So it should be 2/3 because it lost 1/3 of its mass. So now you have a mass of 2/3. The mass of the sun did not change. And then the distance between these two terms would be 1/4 as much. Now that distance term is a squared term. So when you take a look at all these fractions by multiplying them out, you're going to get 2/3 on the top and you're going to get 1/16 on the bottom. Now you should be able to do this without a calculator, but if you need to use a calculator, go ahead. What happens is this term flips up to the top and you get 2 times 16 is 32 over 3. So the force difference between these is you had an original force of 1 and now you have a force of 32/3, so it's gotten much, much, much bigger. Example A3 says, astrology suggests that the position of the planets relative to the Earth can affect your personality. Examine the difference in gravitational force that Mars exerts on the Earth as its closest approach and its farthest approach. And so people say, okay, well look, on its closest approach, okay, the distance is going to be 50 million kilometers. Okay, so we're just going to call that D. Now, when it's on its farthest approach, that is 8D, because if you take 400 million and divide by 50 million, you get 8. So it's 8 times further when it's at its furthest distance than when it's at its closest distance. So people say, okay, yeah, that could possibly work. But you have to realize that although the force is going to end up being, if we plug it in, proportional m1 m2 over d squared, the masses of the two planets don't change. So we're going to have the force is proportional to 1 over 1 squared, and we're going to have forces proportional to 1 over 8 squared. Now whenever you do that, you see that there's quite a big difference. So for the first one you have forces proportional to 1, and for the other one you have forces proportional to 1 over 64. People say, wow, that's a huge difference. Maybe it does work that way. But because the gravitational influence on a person is so incredibly small, it is more likely that the gravitational impact of the doctor who delivers you will have a greater gravitational force on you than the planet Mars, regardless of the distance. So because of that, you can kind of rule out the fact that the alignment of the planets has an impact on your personality. That right there, people say, well, what about other planets that are bigger than Mars? Yes, they are bigger than Mars, but they're even further away, making them less gravitationally impactful on you. So that was the proportionality. And then this guy named Cavendish came along, and he was able to help Newton out just a little bit. He actually came up with the way to turn Newton's proportionality and take it and turn it into an equality. And he did that by measuring this term g. Okay, the term g is the universal gravitational constant, but what he did is he suspended some very heavy cannon bolts by this system of pulleys and ropes, and he was able to measure very, very slight attraction between these two cannonballs. It was a very sophisticated experiment for its day. But by setting up these systems of rope, he was able to gather just very, very small differences in these angles right here between the ropes. It was actually quite a brilliant design. But in doing so, he was able to measure this term g. Now, we have the universal gravitational formula. It's still usually called Newton's law of universal gravitation, and sometimes it's abbreviated as N log, Newton's law of universal gravitation. Now, the formula is still gravitational force. We're still talking about the gravitational force. This term G is the universal gravitational constant. It is the same everywhere. On Earth, on Mars, on Jupiter, on the Sun, in open space, it doesn't matter. It's always the same. Then you have the mass of object 1 and the mass of object 2. You're going to multiply those together, and people usually get confused. They say, which one's mass 1 and which one's mass 2? It does not matter. Because you're going to multiply them together, it doesn't matter if it's 2 times 3 or 3 times 2. It makes no difference. So just call one of them mass 1 and call one of them mass 2. And then finally you have the distance, and that's the distance between the centers of mass, and that's really important. So whenever you look at this, you have planet 1 and planet 2. Okay, you can't just measure from the surface to surface. No, you have to measure from the center of mass, which is usually the center of the planet, to the center of mass. And that actually adds a little bit of distance, which can change your calculations if you're not careful. Please make sure you measure to the center of mass. So we come to example B1. It says determine how far a satellite must be placed from an asteroid 5,000 kilograms to produce a gravitational force of 10 newtons. So you think 10 newtons, that's like it's like 2 pounds, so it's not a huge force. So let's go ahead and see if we can figure this one out. So what we realize is that we have a mass, and we're just going to call that mass 1 because it's the first one that came up, mass 2, and we have a gravitational force. You always have the value of g. It is 6.67 times 10 to the minus 11th. So now we can plug in. We can say, okay, well, F equals G M1 equals 6.67 times 10 to the minus 11th times 1,000 times 5,000 divided by, we want to solve for this distance, but remember the distance term is squared. Now a lot of times R and D are used interchangeably, so I used R here and D here, but they're the same thing. So what you want to do is you want to multiply these terms together. Okay, when you multiply these terms together, you'll realize that you've got 10 over here and d squared over here. Now, algebraically speaking, I can multiply both sides by d squared and divide both sides by 10. And when I do that, it basically switches the d squared and the 10 terms so that that cancels and that cancels. And now you have a number on one side, 6.67 times 10 to the minus 11th times 1,000 times 5,000 divided by 10 equals d squared. So you realize that that equals 0.0003335, but that's the d squared term. A lot of times, for some reason, people forget that this is a d squared term. You don't want d squared, you want d. So you got to take the square root of both sides, and you get that the d is 0.00577 meters. Now you should realize that that's a problem, because if you have an asteroid and you want to place the satellite that far away from the center of mass, that's so close that it's going to be inside the asteroid itself, at which point it's not really going to do anything, so it wouldn't really work. So now, we have a 500 kilogram satellite that moves past an unknown mass, so this is what we don't know. It says the satellite experiences a force of 2 newtons whenever it's 100,000 meters from the object. We want to know what is the mass of the unknown object. So we have a mass 1, we have a distance, and we have a force. Remember, we always know g. Okay, so we can use the equation F equals G M1 M2 over d squared. We plug in our numbers. You get 6.67 times 10 to the minus 11th times 500 times m divided by 100,000 squared equals 2. Now at this point you should realize that you've got to isolate this variable. So what you're going to end up doing is you're going to end up multiplying both sides by 100,000 squared and dividing both sides by 6.67 times 10 to the minus 11th times 500. Basically what you take on the top right here and put it on the bottom right here. You take what was on the bottom right here and you put it on the top right here, and that will cancel everything out. So what you're going to end up with is 2 times 100,000 squared divided by 6.67 times 10 to the minus 11th times 500. Now whenever you do this, make sure you put that bottom part in parentheses. And when you do that, you should get that the mass of this asteroid is approximately 5.99 times 10 to the 17th kilograms. Now it's really important that you do this calculation. You need to be able to do it on your calculator whenever you have a quiz. What is the gravitational attraction between ice skaters separated by 0.5 meters? It says the man has a mass of 60 kilograms while the woman has a mass of 45 kilograms. You should be able to figure out entirely on your own that the gravitational force between the two of them is 7.2 times 10 to the negative 7th newtons, or basically non-existent. Okay, so gravity and motion. So gravity is like any other force in that it can cause an acceleration. So Newton's second law is always the link here. So if you have the gravitational force, you can use Newton's second law, and then you can apply the appropriate kinematics equation. So we're going to work out just a couple examples. Now, the first one says two asteroids, each with a mass of 1,000, are separated by 1,000 meters. If the asteroids are initially at rest relative to each other, how long will it take them to collide? So I'm going to work this out for you just to kind of show you what it looks like, and then we're going to talk about the question because there's an issue with it. The first thing you want to do is you want to be able to calculate the gravitational force between these two things. So we're going to use Newton's law of universal gravitation, and we're going to say F equals 6.67 times 10 to the minus 11th times 1,000 times 1,000 divided by 1,000 squared. And so the math works out perfectly in that these terms cancel, and the gravitational force is 6.67 times 10 to the negative 11th newtons. So now our link between the gravitational force is Newton's second law, so we say F equals ma. Or in our case, it would be 6.67 times 10 to the minus 11th equals 1,000 a. Divide both sides by 1,000, and what you get is a is equal to 6.67 times 10 to the negative 14th. And now we're in meters per second squared. Now the question says, okay, now that you've got the acceleration, how long does it take for it to collide? Realize that each asteroid only has to cover half the distance. Okay, we're going to assume that this distance from the center is negligible at this point. So you would say that it is initially at rest. You would say that you have an acceleration of 6.67 times 10 to the negative 14th meters per second squared. You would say that the distance that you have to travel is 500 meters because it only has to travel half the distance. The other one will travel the other half. And then finally you can solve for the time. You would choose the equation that does not have final velocity in it, and that would be the equation delta D equals VIT plus 1/2 AT squared. Okay, when you plug in, you would get 500 equals, this VIT term would zero out, 1/2 6.67 times 10 to the negative 14th t squared. Whenever you solve for the time, you would rearrange and you would get 1.22 times 10 to the 8th seconds. Okay, now there's a couple of problems with this right now. Okay, the first one is obviously in the sense that we had some assumptions. We had an assumption that this distance to the center of mass was basically nothing. And then we had another assumption here that it accelerated at this the entire time. Now that's a big assumption and it's a big problem because it turns out that's not the case. As these things get closer and closer to each other, it turns out that the acceleration increases. This is one of the reasons why Newton had to invent the new branch of calculus in order to solve this particular problem, because he had a constantly changing acceleration. Okay, this would actually involve, if you were going to do this, it involves a calculus procedure called an integral. And if you take an upper level physics course, either an AP class or a university level physics, okay, you're going to have to do these sorts of things. But this sorts of problem, the reason why I wanted to show it to you is because it does Newton's law of universal gravitation, it does Newton's second law, and then it does if that. You have to be able to use these three in combination to get what you want for a more realistic example. Okay, here's another example of using two formulas, or three formulas in this case. You have the mass of the sun, you have the mass of Earth, and you have the distance between them. And it says it can be approximated as circular motion. So now you can go ahead and figure out what the velocity of the Earth is around the sun by using F equals G m1 m2 over d squared. When you plug your numbers into that one, you should get a force value of about 3.5 times 10 to the 22nd newtons. Then you'll take that force value and you'll plug it in with the mass of Earth and F equals ma to solve for the acceleration of Earth. When you do that, you should get a value of about 0.05899 meters per second squared. Now, the last step in this case is going to be to plug it into a circular motion formula. Remember, centripetal acceleration is what you use when it moves in a circle. It's a equals v squared over r. Okay, whenever you plug the numbers in there, you should get a velocity. Go ahead and scroll down a little bit. The velocity should be about 27,500, usually 500 meters per second. It's going to depend on how you round. It could be up to 28,000. It could be down to 27,000. So realize that you should be able to do this and get these three numbers with your final answer being about 27,500, 20,750. All right, the last question says, what would the acceleration due to gravity be on Earth if the distance from the center to the of the Earth was increased to 10,000 kilometers? Right now, it's about 6,378 kilometers. So, if you were to take a look at the equation, F equals G m1 m2 over d squared, remember that this F is the same F as in F equals ma, or F equals mg. So what I can do is I can set these two things equal to each other, and I can say mg equals g m1 m2 over d squared. Now, this mass right here is the mass of any object on Earth. It will cancel with its counterpart. The mass of Earth does not go away. These g's do not cancel out because they are not the same. You have a lowercase g and a capital G. This lowercase g represents the acceleration due to gravity on Earth. The capital G is the universal gravitational constant. When you plug your numbers into this particular problem, you should be able to get that your acceleration due to gravity is 3.99 meters per second squared if it is 10,000 kilometers. Make sure you look at kilometers.